Rotate your paper 90 degrees and let's answer this Northamptonshire question. So, in 1977 in Northamptonshire, England, David Purley's race car crashed and his speed dropped from 174 kilometers per hour in 0.66 meters, in about this distance. He had 29 fractures, 3 dislocations. His heart stopped 6 times while he was on the operating table, but he survived. As far as we know, this is the biggest acceleration that a human being has survived from. How many G's did he experience? Has nothing to do with today's lesson, but it was nerdy and it was cool, and I came across it when I was creating this lesson, and you probably kind of wondered. So, hey, what was V initial? 174 what? Okay, so 174. Who remembers from last year, how do I go from kilometers per hour to meters per second? It had something to do with the 3.6. Times or divide? I've heard times, I've heard divide. I'll show you how you don't have to memorize it. I'll show you how you can figure it out. You do have to remember that it involves a 3.6. So Jordan, I'll pick on you because you haven't seen this trick. Jordan, have you been on the freeway before? What's the speed limit on the freeway? Not on the highway, on the freeway. It's a lovely, nice round number. No, a lovely, nice round number. A lovely, nice round number. 100 kilometers per hour. Okay? Now, if I want to, listen up. If I want to go from kilometers per hour to meters per second, do I divide or do I times? If I times, what's 100 times 3.6 in your head? So that would mean that I'm going 360 meters every second on the freeway. That would mean every second on the freeway, I'm covering 3.5 football fields. Am I? So do I multiply? No, I divide. And that's, honestly, I do that in my head. I figure that, I use that trick every time. I've never bothered memorizing whether I divide or times. Every time I sit on the freeway at 100 and I go, do I time? No, I divide. So, divide by 3.6. How many meters per second is that? 48.333? I'll go 48.33. What else do I know? Oh, I know V final. What? Huh? You're right. 0, stopped, right? I know D, 0.66. I'd like to find the acceleration. I'm looking for an equation that has V initial, V final, D, and A in it. Don't all rush for your formula sheets at once or anything. Can you get the A by itself, please? Zero squared minus 48.33 squared all over 2 times 0.66. 0 squared minus, answer button squared, divided by 2 times 0.66. Are we speeding up or slowing down? So am I expecting a positive or a negative answer? Negative acceleration? And we get that. Negative 1,700 and I'll go 70. Now, that's not what the question asked. The question asked how many G's that is. If you know the acceleration, how do you change that into G's? Okay. Divide by 9.8. As far as we know, on record, with instruments that we were able to measure ahead of time, because we could tell the speed from the film footage, this is the biggest number of G-forces that a human being has successfully survived and lived to tell the tale. 181 G's. Again, that's the equivalent of having 180 people dogpile on him in a big column. He survived. Is approximately equal to 181 G's. Negative 181 because we're slowing down, but you usually don't put a sign on G's. Yep.
Can you make a fuller
I haven't been able to track that down. I got this from, I have a book, I think it's called Mad About Physics, and it's just full of nerd trivia like that. And one of these days, I want to go through the whole book and add a bunch of the trivia to the lessons, because I find stuff like this interesting. I just haven't got around to yet. So I don't know what, you could Google David, what's his name? Perley. I'm willing to bet there's probably an article somewhere now. Okay. There was a Air Force doctor back in the 50s and 60s who was part of the team that was testing ejection seats for pilots, because we didn't know whether pilots could survive ejecting at faster than the speed of sound. And so he did many, many rides on a rocket sled where he would slam into a cargo net at the end of the rocket sled and decelerate very, very fast. So he regularly dealt with 40 to 50 Gs without permanent damage, although I think he eventually, because one of the things that happens is your eyeballs, because they're full of fluid, the fluid sloshes forward against your eyeballs, and over time his eyeballs stretched a bit, and so he had to get prescription glasses. He permanently, I guess, damaged his eyes. So 50 to 60 Gs, also dangerous, but Naomi, survivable, probably with major intervention, but this guy survived that. You ready? Let's get to the lesson. Work and energy. Work is a scalar. It has a definition. We have to be very careful, Mac, because unfortunately we use the word work in English, and in English it does not mean what it means in physics. When you say in English, I'm working hard, I'm doing work, what you really mean is you're sweating, you're tired. And work has nothing to do with tiredness. It's a physics construct, it's a physics definition mark, and it's defined as the product of the force component times the distance component in the direction of motion. Work is force times distance. Who remembers what were the units for work? Well, first of all, it would be a Newton meter, because force times distance, but we've given a Newton meter a special name. Who remembers what we measure work in? Joules. How much work do you do when you lift a 35 kilogram mass to a height of 1.5 meters? What's this question asking me to find? Work. Work equals force times distance. The key word in this question is the word lift. When you lift, which force are you doing work against? So this would be Fg times distance, except what have we been doing in the last unit? How do I calculate Fg? Mg. And you can call it distance, although when we did this last year, we called the vertical distance h for height. You may recognize, oh yeah, the mgh, I've seen that before. So, mass 35, G 9.8, 1.5, times 9.8 times 1.5. I get 515 joules. How much work does a hiker do on a 50 kilogram backpack if he carries it to the top of a 750 meter mountain? Okay, when you're carrying something up a mountain, which force are you doing work against? It's meant to be real obvious. Gravity. Is gravity in the same direction as the mountain height? Yes? Yeah. Are we doing work then? Yes. If I had said, how much work does it take to carry a 50-kilogram backpack 750 meters along a flat field, the answer is none. This is what I want to beat out of you, Mark. The idea, work is tired. No, it's not. Work is changing an object's amount of energy. But here, it is MGH. 50 times 9.8 times 750. If you carried a 50-kilogram backpack, which is pretty heavy, that's about 120-ish pounds, maybe a bit more, to the top of a 750-meter mountain, 3/4 of a kilometer high, how much work? Do you get 367500? I'll go 3.68 times 10 to the 1, 2, 3, 4, 5 joules of work. Example 3. A ball on the end of a rope is swung about in a circle because of a constant force exerted on the string, like this. How much work is being done on the ball by this force? Well, look at the picture. What direction is the force? Towards the center. What direction is the motion? Towards the center? How much work is being done? At 0. I'm not changing the amount of energy that this ball has. Again, this bugs people, but Naomi, I want you to realize work has a very, very specific physics definition. The force and the distance must be in the same direction. Work is a scalar, but Eric, that doesn't mean it has to be positive. It can be negative. All that means is if you get negative work, you lost energy. Positive work, gain energy. But those are both magnitudes. Lost energy, you have less, not a direction. But in general, a force in the direction of motion does positive work because it tends to give energy to the object. A force in the opposite direction of motion does negative work because it tends to bleed energy from the object. Like that picture there. So it's below, but on the next page, I guess. So, although work can be positive or negative, it's not a vector. Has no direction. Example 4. A child is pulling a wagon along the driveway, exerting a force F along the handle at an angle. How would you calculate the work done by the child on the wagon? Did I say angle? What might you think then? Components. In fact, what we would do is we would say, okay, here's the applied force, which can be broken up into Fx and Fy. There's angle theta. Which trig function could I use to find Fx? Cos. In fact, cos theta equals Fx over F applied, adjacent over hypotenuse, right? Hey, how would I get the fx by itself? What would I do that f applied? Sorry? Times it over? So you know what? Cross that out, put the f applied right there. And in fact, what that does is that shows you the actual formula for work is force times distance cos theta. When you're flat on level ground, what's theta? What angle is when you're flat? To be really obvious, how many degrees is flat? None. 0 degrees. What is the cosine of 0? Can you try that on your calculators, please? What? Did you predict that? Sorry? Oh, you knew it? Yeah, you know what? In other words, when you're flat, cos theta, cos 0 is 1, and it's force times distance, physics 11. But the extension is Mac in physics 12. Okay, if you do have an angle, it's a component, it's cos theta. Oh, what about when you're 90 degrees, like Mark and his piggyback? What's the cosine of 90? What's the cosine of 90? Jordan, what? So what's f times d times 0? Okay, there's one more way, Mark, where I'm telling you, you were not doing any work on Rob with the piggyback. Okay? What if the force is not constant? Well, turns out work is also the area under a force versus distance graph. So here's a graph. How much work is done moving this object from 2 meters to 6 meters? I don't know. Oh, what kind of a graph is this? Okay, so first of all, work is what times what? Force times distance. Work is also area under a force versus distance graph. By the way, you're going to end up with 3 definitions of work in this unit. Only one of them is on your formula sheet. The force times distance is the only one on your formula sheet. The other 2 you're going to have to kind of memorize, but I'll flog them to death so that by the time we're done, Anita, you'll be okay. Okay? Anita, what's this asking me to find? How much what? Work. How much work is done moving from what to what? Moving from... Okay, you see the question? I'm going to tell you what the answer is as a picture. As a picture, it's that area. Hey, what shape is that? Jordan, trapezoid. I always ask, because I'm a nerd, does anybody know the formula for the area of a trapezoid? There is one. I've had only once in about 10 years where I had a kid that knew it. Anybody know it? There's a reason you don't. It's cool, but it's redundant. Because not only is this a trapezoid, Jordan, I'm going to argue that this is also a rectangle and a triangle, and I have formulas for each of those. How much work? It's the area. Work is going to be area 1 plus area 2. What shape is area 1? Rectangle. What's the area of a rectangle? Length times width. What's the length of rectangle 1? Don't say 6. 4. What's the width of rectangle 1? How far from here to here? It's supposed to be 2. It's a sloppy drawing, but it's meant to be 2. Plus the triangle. What's the area of a triangle? By the way, this one's actually on your formula sheet, so if you blank out, it's on there somewhere. Mark. It is base times height divided by 2. What's the base of triangle 2 there? What's the height of triangle 2 there? Don't say 3. 1, right, from here to here. Divided by 2. I'm even going to argue you don't need a calculator. What's 4 times 2? What's 4 times 1 divided by 2? Right? How many joules of work was done in moving whatever object this is, Anita, I don't know, but how many joules of work was done moving this object from 2 meters to 6 meters? 10 joules. 10 joules. Jenny, work is what times what? Force times distance. It's also, it turns out, the area under a force versus distance graph. By the way, do you see why I couldn't go force times distance? Is the force constant? At 0, how big is the force in newtons? 1 newton. By the time you get to 2 meters, how big is the force? 2 newtons. By the time you get to 6 meters, how big is the force? 6 newtons. Something wonky going on there. This is a changing force. Changing force. Energy. Energy is the ability to do work. There are many, 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 many forms of energy. First is the energy of motion. It's one of the ones we're going to be looking at quite a lot this unit. Who remembers what we called the energy that all moving objects possessed? Kinetic energy. Another form of energy is heat, created by friction. Gravitational potential energy, this was the energy possessed by an object due to its position. Usually we symbolize that, or at least I did, as PE. We'll come up with an equation for that a bit later. Chemical potential energy. So potential energy is stored energy. There are many ways to store energy. One is gravitationally, by lifting something up and letting it hang there. You've given it some extra energy. Chemical potential energy, explosives, food. Those are all forms of chemical potential energy. Other forms, sound energy, elastic energy. You can, when you stretch a rubber band, you're storing energy in it. Nuclear energy, stored in the nucleus of an atom, etc. Turns out sometimes when we do work, we make things move. Fill in the proof below to find an expression for motion energy. Okay. Eric, gonna make it? Yeah. Okay. Okay. Eric, work equals what times what? Let's write that down. And even more fundamental, force equals what times what? F equals? So I'm going to replace the F with an MA, and then the D drops down. Yeah, we have work equals mad. Work makes me mad too. No, it's not a makes me mad. Work, MAD. And then I'm going to get a little bit clever here. I'm going to put, for reasons that will shortly become clear, 1/2 in front of the M, and then a 2 in front of the A. So I have a 1/2 M bracket 2AD. Have I changed this? No, if I times by 2 while at the same time timesing by 1/2, what have I really multiplied everything by? 1. So have I changed anything? No. Why did I do that? Well, since VF squared equals VI squared plus 2AD, assuming we start from rest, what can I replace 2AD with? VF squared. Assuming I start from rest, I can replace the 2AD right there. Whoop. I can replace this with, and the 1/2 m drops down. And so what's my expression for kinetic energy? 1/2 mv squared. Mac, there's where it comes from. It's a fairly simple derivation. Mickey, do you need to know how to derive that? No. But it's kind of nerdily cool on the scale of nerdiness. So, this is what we're going to put in the big box here. You want to find out how much motion energy a moving object possesses? It's going to be equal to 1/2 times its mass times the square of its speed. Do I put vector symbols on here? Nope. Why not? Because like work, energy is also a scalar. Nerd note, just to give you an idea of how much energy there is in a jelly donut, it's about 10 to the 6th joules, about 1,000,000 joules. And a mosquito push-up, for a mosquito to do a push-up, takes about 1 erg of energy, which is about 10 to the -13 jelly donuts. Just giving you some context. Next page. A golfer wishes to improve his driving distance. What would have more effect? Doubling the mass of the golf club or doubling the speed with which the golf club strikes the ball? Convince me. So you're saying this because, what was your argument, Mark? Okay, so let's write down, yeah. You can double the mass? What's the equation for kinetic energy, Rafi, my joy? Kinetic energy equals what? Okay, now, there's 2 possibilities, doubling the mass or doubling the speed. Once you've written that down, put your pencils down. If I double the mass, I would get this. That's doubling the mass. If I double the speed, I get this. What? What? See the squared? So pick your pencils up. There's my proof, pointing to the squared. And Jordan, this is why over the past 20 years or so, sporting equipment, golf clubs, tennis rackets, baseball bats, hockey sticks, have they become heavier or lighter? Lighter. It's a trade-off because a bigger mass does also help you hit it further too, but a faster velocity, you're getting a squared reward back. And so the trade-off is, hey, if we can make it lighter, but you can increase your racket speed or your club head speed or your swing speed, that's way more bang for your buck. Way more bang for your buck. If you ever find at a garage sale or in your parents' or grandparents' attic or something like that, like a wooden tennis racket from the 1970s, and if you play tennis, how the heck did they even swing these things? Or if you find an old hockey stick or an old set of golf clubs, how the heck did they even swing these things? They're massive. Can't get any club head speed. Eric, you're not foolish looking at your phone or anything like that, are you? Okay. Strange, but okay. So Eric, kinetic energy is 1/2 mv squared. That's the energy of motion. We also said there's gravitational potential energy. Let's see if we can fill in a proof, you and I, for that. So I said sometimes when we do work, we lift an object and we give it height energy. Fill in the proof below to find an expression for height energy, which I'm going to call PE for short. Even though there's many, many, many types of potential energy, because the most common one we're going to be dealing with this year, I'm going to say, if I talk about potential energy, assume it's gravitational unless I say different. So you ready? Eric, work equals what times what? Work equals what times what? If you're lifting something, which force are you lifting against? So Fg, what was our equation last unit for Fg? More specific, when we were talking about gravity, in other words, when I did a free body diagram. And you know what? Another expression for a vertical distance is a height. There's the mgh derived in just one line with Eric's help. Potential energy is mgh. Also measured in joules. Do I put a negative 9.8 in here? Why not? Scalar. Okay. Usually, we'll be focusing on mechanical energy, which Rafi has two types, kinetic and gravitational potential. Kinetic and potential. This brings us to our third definition of work. Jenny, work is what times what? Work is also the area under a force versus distance graph. But the best definition of work, the one that actually allows me to answer more questions, is the Work-Energy Theorem. And it says this: the net work done on an object is equal to its total change in energy. Work equals the change in potential energy plus the change in kinetic energy. Sometimes you'll see textbooks give a lousier version of this. Sometimes you'll see textbooks say that work equals the change in kinetic, but that's only if the object isn't changing height, if the object is traveling on flat ground, because if you're starting on a height of 0 and ending on a height of 0, what's your change in potential energy? Nothing. So I've seen it simplified to that, but that is not the Work-Energy Theorem. In fact, I have one textbook that calls that the Work-Energy Theorem, and one of the reasons I stopped using that textbook was just because of that, in my mind, preventable error. This is the Work-Energy Theorem. So you ready, Josh? I'm going to pick on you a little bit. Example 7. What are they asking me to find? Work is what times what, Jenny? Read the question. Do you see a force or a distance in the question? No. What would I be looking for? If there was a force, what units would I be looking for? No, if there was a force, what units would I be looking for? Begins with letter N. Newtons. Do you see newtons anywhere? In other words, you're doing this, we can be much faster. You're overcomplicating this. See newtons anywhere? See meters anywhere? So work is what times what? Can't use that definition. Work is also the area underneath a force versus distance graph. This may seem obvious, but do you see a graph? So can't use that definition. Then I have to fall back on my third definition. This is how, Mickey, I do all of these. When they say how much work, well, force times distance, I always check that. No. Area under it, no graph. That's how I know to use the Work-Energy Theorem. What's the Work-Energy Theorem? Work equals change in potential plus change in kinetic. Does this question imply that there's a hill or a change in height involved? Then you know what? What's change in anything? Final minus initial. Work is going to be, okay, what's our equation for kinetic energy? Kinetic energy equals what? So kinetic energy final, I guess, would be 1/2 mv final squared minus 1/2 mv initial squared. By the way, are any of these 0? V final. Oh, so you're saying I can do that? So it's going to be just negative. The negative is coming from the fact that the car is losing energy. A half. What's the mass of the car? What's the initial speed of the car? Check the units. Are the units correct? 32 meters per second. How much work does it take to stop this car? Do you get negative 614,400? Yes? No? Negative 6.14 times 10 to the 1, 2, 3, 4, 5 joules must be lost or removed from the car. What force is doing the work? Think about it. I heard it. What? Friction. Where is the energy going? Where is most of the energy going? To the point where, in fact, we have to be careful when we're driving on a long hill. Where is most of the energy going? It's heating up the brakes. And on a long hill, you can overheat your brake. The energy's got to go somewhere. Can't just vanish. So where's the energy going? It's heating up the brakes. Some of it might be heating up the tires in the road. Yeah. A 19-kilogram artillery shell is launched from a cannon. At the top of its arc, it reaches a height of 245 meters with a horizontal speed of 95 meters per second. What's the minimum amount of work that the cannon did on the artillery shell? Okay. Hey, Shaq, work equals what times what? Okay. Read the question. Do you see a force anywhere? No. I do see a distance, but do you see a force anywhere? So I'm not going to use force times distance. Scratch that one off. Oh, work is also the area underneath a force versus distance graph. Hey, Rafi, see a graphy? No. What's our third this is, again, I'm telling you how much work. You all spotted that. This is the checklist I go through. First I see, can I use force times distance? No force. Is there a graph? No graph. Then what's our new definition of work, Rafi? What did I write at the top of the page? What's the work-energy theorem? Work also equals what? Where, what's change in anything? What's change in anything, folks? Always final minus initial, worth memorizing. So this is going to be PE final minus PE initial plus KE final minus KE initial. Are any of these zero? PEI is nothing? Don't let them hear you that out east. Oh, you mean the potential energy initial is zero. You're not denigrating our smallest province. Oh, because we're starting on the ground, Grayson, I think we can say no initial potential energy. What else? Well, the fact that I said minimum, let's assume we started from rest. How much work is required? It's going to be PE final. That's going to be MGH final plus KE final. That's going to be a half MV final squared. Mr. Dueck, how dare you? What? Mr. Dueck, H is vertical, but the V in the second expression, it clearly says is horizontal. And you yelled at us so much about putting verticals and horizontals into the same equation. Mr. Dueck, how dare you? Scalar. Couldn't care less. It's a scalar. Who cares about direction? It's a scalar. Get over it. Did they give me the mass? G, 9.8. Height, 245 plus 0.5. Mass, 19. Horizontal speed. I need at least this much work, this much energy to get the shell to do this. Maybe more, because there could have been also still a vertical, you know what? There could have been air resistant, there could have been other dissipative energies and forces. You get 131,356.5? Did I miss a square? No. Am I right? Yeah. So 1.31 times 10 to the 1, 2, 3, 4, 5. Units work. Joules. Where'd that energy come from? Where'd the energy come from? Sorry? The gunpowder in the cannon, if I was going to be really specific, right? Assuming it's a gunpowder artillery shell. It's your homework. Number 1. A and B. I haven't done efficiency yet. 4 is good, except can't do 4E. Six is good. Apparently I skipped 5. Nine is good. I'll pause there.